shaped, right? Physically or even logically. Sometimes in some kind of situation, we can talk about a logical topology instead of a physical one. Okay, and we'll give an example about that. So you see here we have many shapes that a network can have. Of course, there is some that they are now dedicated in some technologies we still use them, others that they are deprecated and so on. The first one, for example, is the star, like this one right here, as you can see. So the concept of the star is when we have a centralized node. Okay, so we have a centralized device and everything is connected one by one to that central node. Now it's the standard of the LAN. When we talk about local area network, those company, enterprise, home, whatever internal network, you will end up usually with the star, right? Before it was a bus one, and we even used the ring in there before, right? But now, since we have these switches, we are using the star topology, and each topology have some advantage and disadvantage compared to the other one. So let's talk about this star topology here. So advantage of star topology, it's easy to install and wire. You see, it's clean. So each device have to go as a source and destination that central node. Like for example, our classrooms are all on the star topology. You're gonna have a switch in each classroom, and all the computers of the students gonna have one personal cable from that device going to that switch. It doesn't mean that we need to shape our classroom like this, right? So we need to put the switch in the middle of the classroom, and we have to put the tables of the students shaped as a star like this. No, not at all, right? So don't be tricked by the name of the star. It doesn't mean that you're gonna see a star in there. Our classrooms usually they're gonna have a switch in the corner somewhere, and cabling going through the wall and distributing to the table of the students, right? Like this. And we're gonna have all the cables here going to the other side of the classroom, and we have another distribution for the tables of the computers of the students, right? So this one, see that it's not really shaped as a star when we see the classroom from top, but it's a star. Why? Because of each device have his own cable and go into that central node. Okay? So don't really take on consideration that physical topology is a star. You need to shape it as the form of the star. The concept is the star, right? So the concept of it is when you have a central node and you have cables going everywhere to each device, a camera, a printer, a server, whatever, right? I can have here, for example, a printing device, and I have a cable here, and so go on and so go on. So you're gonna find a door where you're gonna go enter to the classroom, the office of the teacher. Here's the board here, right? And the office of the teacher gonna have his own distribution also, another cable going here. They have a computer. So when we come to the classroom, you see we are here. This is the board in front of us, and we have in each side some tables with computers. And it doesn't look like a star. This is so different from this, right? This is not equal at all. But the concept is the same. You see, so when we have a star, each edge here is connected to a central thing, right? So the concept of it is exactly the same as this one. This is why we call it a star. You don't have to shape all the office in the world in this form, right? So you can have just one router at home, and it's going to another room here, connecting to TV. That router have a switch also, of course. and so go on, and just go into your office. You have a computer and you have some Wi-Fi device, right? So I have a tablet here, I have phones, but each one has have his own connection, as you can see here. So each one is going by his own connection to the to that central device. That central device that is connected to something after and going to a router or whatever. But this is the same concept as those edges of the star, that they all have their own connection with this central point, right? This central node. All right, this is the star. Now, what is the advantage of having that? As you can see, it's easy to install and wire. Not really complicated. Well, the more it's bigger, the more it can become complicated. But each device or each part of this network is isolated. Okay, it's isolated. So we have no disruption to the network when we connecting or removing a device. You see, if I add a new device right here, so I'm gonna bring another computer and I will just connect it. I don't have any disruption to the whole network. My network still work. If I'm gonna remove something also, it's still fine, right? We don't have any problem with that. So it still work properly without any problem. So removing device, adding device doesn't have any impact on our network. A disadvantage require more cables length, the more it's bigger, right? We need more cables here. The more it's bigger, the more we're gonna need cables and so on. One of the big disadvantage of this star, you see this central node here. If it fail, everything is gone, right? So if we have a problem here, are we gonna have a problem everywhere? But if we have a problem in any separated device, we don't have any problem in the others, right? So we don't have any impact of removing, adding, or troubleshooting here. It's easy, you see. So if this device is not working, I know that the problem is in the device, the problem is in this cable, or the problem is in this port, maybe, right? Because of the others are working, right? If everything shut down, well, I know that the problem is centralized here. So I have this quick analyze of the problem quickly, right? So it's easy to troubleshoot. It's not complicated to troubleshoot. This central device, before we were using hubs. We're going to talk about them, right? Now we are using switches. Now we are using switches. So if the hub or the switch or a connector here fail from outside, the one that connects to the outside, not attached are disabled, more expensive than the linear and the bus. It doesn't mean that it's the most expensive, but if we compare it to this line or bus, it's more expensive. The bus topology. So the bus topology, I'm gonna have a backbone here, right? So a centralized bus, a centralized cable that's gonna distribute to all the computer, right? With a node. One node is the distance from one device to another device. Could have a server, could have a printer. It used some extra technology here that we call them terminators at each extremity of our network, right? So this one is a linear, like this, right? So we have that bus cable. It's gonna distribute all the communication inside that network. Of course, this one is deprecated. Here we use the coaxial cable with BNC connectors, and also we need to put some money more and use these terminators, right? So terminators are in each extremity to kill the signal, otherwise the signal will come back here and we're gonna have a mass of communication here. So if because of in reality how these things stand, so in each node we're gonna double that data, right? So this computer, when he want to talk with this one, for example, right? So from here to here, he don't know if he's here or here or here or whatever. It's just devices that they are connected to this backbone. So when we send something, we're gonna have exactly the same data that go in this direction and in this direction. Now it's gonna reach another node, right? This data will be sent here and 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 sent here till we're gonna find the identifier, the identifier of that device of the destination that he's gonna answer. But you see, as all the others received exactly the same message, so here also will be send and send and send. So we're gonna have always a signal going from here and here. So this is why we need a terminator. So when anything gonna reach those devices will be killed, right? The signal will be dropped. Sir, any update regarding college opening? I don't know. Sincerely, Aryan, I have no idea. Well, we received an email that maybe they are putting on consideration those stuff of coming back or whatever, but I didn't really care about it. So I was really busy. We don't have any orders yet or something clear or whatever. Okay. I think that now the government, it's not the college, it's about the government. Now the government is allowing students come in there, I think 50 or something like that. And so even if they will come back in there, will be not like the regular classrooms. Well, we're going to talk about it after. Right? Just focus in the class now. And all right. So this is the bus technology. This is how it's shaped. Before we were using this, before having those switches here, we were using this on LAN, on local area network. This is how local area network has used to be before. And the disadvantage and advantages of this. So advantage of linears, it's easy to connect a computer or peripheral to a linear bus. We just take the cable and connect it on that backbone. Require less cabling on this one, right? So I have a central cable and just distribution after. Disadvantage of linear bus: so entire network shutdown if there's a break in the main cable. So you see this cable here? If there is a break on this cable, the entire network is gone, right? So if there is a problem here, the entire network is gone. Terminators are required compared to the others. We need also extra configuration and extra devices in here and here, right? Difficult to identify a problem if the entire network shut down, right? So if everything shut down because of this one, if this device is not working, everything is not working. If there is a problem here, everything will not work, and so go on. So imagine if everything is not working, it's gonna be really difficult to know where is the problem. Maybe here, maybe here, maybe here, maybe in the backbone, maybe in the terminators, maybe in something, right? So it's much more difficult to troubleshoot. This one is much more difficult to troubleshoot. I'm not taking a bus and metro to go to class with a new COVID strain popping out of nowhere. Well, Mari, nobody gonna force you. I don't think that they're gonna do that. Me neither. Just to uh, just to make you sure, right? So, well, I'm gonna talk about it after, as I told you. We have a star bus. So you see now we can merge those things here. For example, if you have switches that they will be connected as a bus, one to another one to another one. Okay, and each switch gonna be on his own distribution node, right? So this is a star, this is a star, this is a star, but as you can see, all of them are connected as a bus here. This is one of the main topology in buildings, in companies, in whatever. As for example, at Herzing, you see that, well, it's a little bit different because our switches go one by one to the router, right? So it's much more than this here. Right? But each classroom is a star, and that switch go to one router, and that router is routing all the classrooms. Okay, so this is it's a little bit different than this one here. But it's the same concept. I mean, many stars that they are all connected together. We have the ring, the token ring, or the ring. The ring, as you can see here, is kind of bus, but instead of putting terminators, we're gonna close that thing, right? in a circular way. And it's completely different, even the configuration, the protocols that we are here. So we use tokens. The frames are completely different than the other one. But as you can see, it's closed. Well, one of the big disadvantage of using this circular thing is we don't have collisions, right? Because of always the packet gonna flow in one direction. So even if this computer want to talk with this computer, well, let's say for example, this is the direction of our data, right? So if this computer want to talk to this computer, he need to send to all devices till he gonna reach that one. We have high speed here because of the protocol is much more simple, and we don't have collisions, right? We have some advantage in the speed and the organization of the packet, because as I told you, they flow in one direction, not like this one here. So the switch can talk to the computer can talk to the switch, so we have two directions of data everywhere. In this token ring, it's always one direction, so we don't have collisions, and this is a huge advantage, right? So advantages: all data flow in one direction, reducing the chance of packet collision on have packets. This ring here, he gonna have tokens, so it's like an empty trucks, right? And each computer, when he want to send something, well, he gonna catch one of those trucks and put something on it and send it back and put it back on the highway, right? So those are called tokens. It's just a code, right? It's not really physically something that we put something in it. It's just a token, some empty frames, if you want, just headers going and going and going. So we're gonna catch that and put the data on top of that and put it back on that token ring. But the main idea here is that the data always flow in one direction, and we don't have collisions. A network server is not needed to control network connectivity between each workstation. Everything is automatically done here, just flowing the tokens, and that's it. Data transfer between workstation at high speed. So we have an advantage of some speed here on the concept. Disadvantage of ring: all data being transferred over the network must pass through each workstation or each nodes here. See, it's not really secure. Needs strong encryption, needs strong things. So otherwise, every device here need to see the data and send it to the other one, and this one gonna catch it and send it to the other one. Of course, it's slower than the star topology when we use it in a LAN, right? Slower than the star topology. In star topology now we can use network cards giga Ethernet, right? So much more advanced. The entire network will be impacted in if one workstation shut down. See, so if I have a problem here, everything gonna be done, right? Everything gonna be down. So there is no more transfer. I have problem in this workstation. Yeah, so my ring is not working anymore. Problem here, my ring is not working anymore. Okay. The hardware needed to connect each workstation to the network is more expensive than Ethernet cards, hubs, and switches. Right? So we need a MUI here. So we're going to talk about them quickly also in module 5, next module. That to connect one node or one phase to another phase to another phase also, and those devices. So we need to spend more money on those kind of devices that we don't need in the star here, for example. So this is the standard of our local area network, right? The star one are the standard now. This one we kept it on the one technology, wide area network. There's many portions of the internet that is still working on this. It's called FDDI, or we have a chapter, or we have a topic on next module about that on double ring, and we use it for fiber optic to cover a wall network on a city or something. So it's small FDDI or a big area from one ESP to another one, and so on. So we still use this technology here, but in the wide area network, much more larger and bigger networks. and based on fiber optic now. So they evolved this kind of communication and of the tokens and adapted it to fiber optic. And in that case, we really have a high speed. The mesh one, so the mesh is when each device have a connection to each other device. Right? For example, if you take this computer, it's connected to this one, it's connected to this one, it's connected to this one, right? This is a partial mesh because of if I do a full mesh here, I need to have a connection from this one to this one, from this one to this one also, right? So this is a partial mesh, as we can see here. So we have this mesh that it's fully connected. You see, each node is mandatory to be connected to each other node with his own connection. This is a mesh or partial one. So as you can see, from each node we have multiple connection, but it's not from each node to all the others, right? This is fully connected. This is just a partial one or simple mesh. So this is not really fully connected. As you can see, this one connected to this one, to this one, to this one. Is not really connected directly to this one, right? So it's still not really fully connected. The mesh have a huge advantage of a high amount of traffic, right? So it can manage high amount of traffic. This one can talk with this one and talk with this one and talk with this one at the same time, or talk with this one through this one, and so on. So we can manage high traffic here because of multiple devices can transmit data simultaneously. A failure of one device does not cause a break in our network at all. So even if this one is done, I still can always find multiple ways to go here, right? So I can still find this way, I can still find this way, I can still find this way and this way and this way. I can go through all of them and like this, right? So if any node gonna break in the network, doesn't have problem at all. We always gonna find another way. We have multiple way, always multiple way from one spot to another spot, right? So it's not like the others here. For example, this one, we can reach it all the way, right? This one want to talk to this one. There's one way in there, okay? But the mesh have this advantage of managing a high amount of data, and the failure of any device doesn't have any impact on the network. Okay, still work. We still always find another way to go from somewhere to somewhere. Okay, adding additional device does not disrupt at all. See, so if I'm gonna just add a new one here, my network still work. I remove one, my network still work, right? Disadvantage, so the cost of this one is the most higher, right? So it's the most expensive because of all these connection nodes. We need to spend more money in the cables, more money in the devices that they are connecting each nodes to each nodes and so on. So we need a more technology, more money. Building and maintaining the topology is difficult, right? It's complicated. We have a lot of things, a lot of connection from everywhere to everywhere, right? So to build it and manage it, keep managing that topology, still complicated compared to all the others. Right? It's not simple. Okay, it's a spider web. The chance of redundant connection is high. Also, the more is complex, the more we can have redundant connection from one node to another, which add to high cost of potential or for reduced efficiency. Also, a lot of transmission here. We can have problem with the packets. Who can give me an example of this one? For example, what is a mesh? And you know it. Internet. Good, Kamaldeep. Internet is a mesh. All right. If you want to reach a website and there is a router that is down, you always find another way, right? If I'm connected to any server in Japan, I will always find multiple ways to go in there, right? Because everything is almost connected to everything with multiple different way to go from that point to the other point, right? So internet is one of the most great example of the mesh topology. Okay, it's complex. Everything is connected to everything, right? But we have this advantage of always finding a way from somewhere to somewhere, finding a different way. Home illustration here. So as you can see, I can have a home router, a switch, separated one, and this is the internet. I'm going to have a star topology inside. Or we can have this kind of combo devices that we have nowadays, right? So everything is included here: the switch, router, DNS server, whatever, a modem in here, and it's still star topologies. They are all connected as a star topology. So at home, usually this is what you have. You have a star topology. Of course, we have devices with Wi-Fi now, wireless, still star, right? That that wireless, what we have an access point, and each device is connected individually to that access point. So it's the same as a star, but wireless. We don't have wires. This is a 3-LAN connected by router, for example. As you can see here, this is the kind of topology that we have in our school. This is a classroom, this is a classroom, this is a classroom, and we have a router, a big router, uh, there in specific room for the administrators, and all the switches go there, right? This is why all our classrooms are different subnets, and they can talk to each other because we have routing in there. So mainly, usually, this is the topology that you're going to find in companies, right? So we have that central node, and after from it, it's kind of star, but it will end up with other stars, right? Other stars with other nodes, and those nodes going to be switches. We can have some hybrid ones. Hybrid is when we mix many topologies at the same time to build a bigger network, right? So as you can see here, I have a bus, a linear one, that's connected to hub, and this hub is connected as a star topology to this one, right? And after connected to hub here, and this hub, and all this is another star. So we mixed some linear bus topology with other stars here, but we end up with those kind of network that we call them hybrid one, right? So those are hybrid. Man and WAN, metropolitan and wide area network. So this is usually how they are. As you can see here, I have a star. This is offices, and this is the first floor. This is second floor, whatever. And they're gonna go to a big router, and this router gonna go to the WAN technology that we're gonna study. This is the main topic of our next module, module 5. We're gonna see what is in this here, right? A lot of things. It's just represented by a cable here, right? But it's not like that, right? There's a lot of things here. So for example, this is on Philadelphia, the other one is on San Francisco router, and we go through the wide area network, and after we end up with another local area network right here. That it's gonna have its own distribution here. So we have a first one, we have a second one. As you can see here, this one is a star bus because we have a switch connected to this switch. So this switch is not really going directly to the router, but is connected to another switch. So this is a star bus here, right? Star bus. We have a bus between these two switches, and each one have his own star here and here. The devices. The devices that we use on this one, on this lens, sorry, the one are a little bit different, completely different, by the way, not a little bit. We used to use hubs. Hubs are those central nodes that we use on the star topology. Hubs are stupid switches. This is what we call them, right? So this is my star here. This is the device, and I have some peripherals that they are connected to this star. Now, if this one is a hub, it's gonna work like some kind of multiple outlet, right? So we're gonna have an input. Well, this guy is talking here, and the hub is really stupid. So he don't care where is the destination. He don't work with the MAC addresses. He don't even identify what is these devices with their MAC addresses. He's not smart at all. He will just multiply these signals in multiple ports, in all his own ports. He don't care, right? So this one is sending. So this guy gonna receive it. This guy gonna receive it. This guy gonna receive it, and this guy gonna receive it. And the one that kind of broadcast, yeah, if you want, right? This is just a kind of multiple outlet. Here is just like we are forking the cable, right? We are just kind of forking the cable physically everywhere. So once this one gonna receive it and this is the destination, of course he gonna answer and it's the same, right? Everybody gonna receive at the same time. So it's not really secure. Bad management here. The hub, if you remember, the OC model, since it's just a fork of the cable, so the hub is working in which layer of the OC model? If we think about it logically. So as I told you, it's just forking first, physical. Yeah, good, Davinder. It's physics, right? It's the same thing here. It's just a device, but it still don't, because of what we have. We have physics, we have data link. Data link, we start using technology. We have frames, and those frames gonna contain MAC addresses, right? And those MAC addresses will identify the computers. Here we have MAC table, ARP, the ARP protocol, and we can identify each one. So when we have a source sending something, we know what is the destination on this data link. We are able to identify what is the destination. Is this one or this one? Is this one? Because this central device already know all the devices and identify them based on MAC addresses. Well, this is a switch. But on physical, as I told you, hub don't work with these MAC addresses. You don't use them. Okay, it's just a forking the cable, something like that. Okay, physically, we're gonna just multiply the signal in all the directions, and after the destination gonna be identified an answer to that message or data or request or payload. So this is hub work on the physical one. This is why we call him a stupid switch, or the switch. Also, sometimes we call it smart hub. It's a smart hub. So it's smarter, because this one was a standard for years and years for the LAN topology. So the star was based on hub, and after we developed the switches and work with the switches now, that they are more smart. They know what is the destination, what is the source, so they don't need to send this message everywhere, right? They need just to send it to the destination, to the destination, because they already know each device that is connected to them. They identify them by MAC addresses. So they exchange the MAC addresses and they know themselves. So they identify the destination, and they process on sending to that only one destination, right? So this is the difference between hub and switch. Okay, the hub is stupid. It's just like multiple outlet, right? So you have that juice coming from the wall. You plug your multiple outlet, and after you have multiple ones where you can plug devices, right? So it's just forking that cable. It's something like that. More than that, but something like that, right? So if we talk like logically about the hub here, sorry, if we talk logically about the hub. So I'm sending something here, and it's every device is receiving that request. So physically, it's a kind of star, right? Because they are all connected with their own cable. But if we talk about this topology logically, how we can see it? If we analyze the kind of transmission from one point to another one, can we say that it's a star topology? Like each one is talking with one place? No, he's talking with everybody. Where did we see that before? forking things, forking the data. Where did we see it? We didn't see it here. I was just talking about it here. See? So when this one is sending, we're gonna fork that data here and here and here and here and here and here till we're gonna find the destination. But it's the signal is repeated everywhere, right? It's the same thing here. The signal is repeated everywhere. So what we can say about this star topology if it's using hub? So the hub logically he's a bus, right? Logically, not physically. Physically, we have this kind of classroom. So imagine this is my hub now in this classroom. It's not a switch anymore. So this is a hub here. So physically, it's a star, right? So each device is connected with his own cable to that hub. But when someone is talking with someone, we are replicating the signal everywhere, kind of, right? So it's working like a bus. Logically, it's a bus. It's not a star, but physically it's a star, right? So this is why I told you sometimes when we talk about topologies, we can also mention this logical topology and physical topology. Okay, you can have a physical star topology by working as a bus topology. Okay, the result at the end is ending with the bus topology here. If it's a hub, but if it's a switch, it's like fully star physically, star logically, because each one is talking just with each one, right? We have one link to another one. Repeaters are devices that we extend the network with, right? So in some destination, we need to amplify the signal again. So as you can see, you have just an input and output. So put it in there, you're gonna repeat that signal in the other port with higher amplification for the signal. So we can extend. We use these repeaters to extend larger LANs. We have bridges also working some kind of same way on this as this one, but on two different networks. They are a little bit smarter than those repeaters. Okay, so they can link to different LANs. We extend LAN to another bigger LAN and so on. We call them bridges. Routers are much more smarter. In which layer the routers work, guys? Which layer of the OC model? So we saw that the hub is on the first layer physical, switches are in data link because they deal with the MAC addresses. And routers, they deal with what? Come on, I'm so disappointed I didn't have any answer yet. Come on, routers. Which layer? We studied that. Layer 3, Chief, good. Okay, layer 3. They deal with the IP addresses. Oh, you need to review your Malhar is IPs. Yeah, of course. They deal with the IPs. Routers, they are the one who deal with the IP addresses too. You don't remember that? When we talked how the packets flow, for example, and I did this. So this is my switch, and after I go to the router, and after I go to a router, and I have a computer here, and I have a switch here, for example, and after I have a computer. So we saw how packets flow from one node to one node. We use MAC addresses to push from one device to another device. We use MAC address to push from one device to another device, and so go on. But how we keep tracking the IP of source, and we know that we should go to this destination, right? Because of these routers, it doesn't mean that they should be connected just with one. I can have multiple destinations, right? Multiple destinations here for networks. This is how things work, right? I can have a switch here and go into multiple devices, computers, and so go on. So how the hell this computer, when he receives the packet at this router, he will know that he have to send it to this way, but not to this way or this router here or another router. He have to send it here because he keep tracking the IPs, not the MAC addresses. Now, after to send it back to the next router, we use MAC or other things, right? If we are in the one, we use other more advanced things that we don't know yet, MPLS or whatever, right? So here, this one, when he gonna receive it and he's connected to many different things, also, how the hell he know that he have to send it here? Because he's a router, he can read the IP source and IP destination, so he deal with the IPs now, right? Much more smarter than the switch. Is the one who link different network IDs. The switch don't do that, right? The switch is designed, or hub is designed to link physically devices. The router is designed to link distant and logical networks area, right? Distant one, so he will always find the way using many different protocols of routing. Switches, they don't have protocols of routings. They just based on their MAC addresses, they can transfer to the physical things that they are connected to them. That's it. Okay, but the router, they always know where we have to send to go to the final destination, because they read the real map, the full picture of that map, and they know where we have to send and go till the final destination, right? So the routers are in the upper layer now. We are on layer 3, and we are dealing with packets. We are dealing with the packets. Here on the hub and the switches is just frames. Okay, we are dealing with frames. Well, the hub is not even frames in there. The hub is just zero ones. It's just frequencies that we are forking it, right? But the switch, we build back to some data frames, and we understand these headers of the frames that we're going to talk about them right after. So we know the information of MAC addresses, destination, source, and we know in which device we need to send that data, right? The router is more than that, more complex than that. We use routing to identify and find what is the best way, what is the best path, the cost of each path, and so on. So we will know what is the best way to go from somewhere to somewhere, right? Based on what? Based on these informations that they are on the EP header, right? The packet header. So IP source and IP destination. The switch doesn't really keep tracking those IPs. Is focusing more on the MAC addresses and the next node. What is the next device, right? This is it. So the switch is more designed to link physically devices around him in one classroom, in one floor, one office, something like that, right? So physically they are linked, they can talk. But routers, he link different networks, distant ones, okay, or different logical. For example, when we started learning how to ping two different network IDs, well, we put in the middle a router, right? He can talk to different logical network. In our case here in Hyper-V, it wasn't really distant, right? It was in between just virtual machines, but I mean the idea behind is the same, right? So he can understand. Okay, this one is coming from 192.168 is going to 10.0.0 something, and so go on and so go on, and he uses several different protocols that you're going to study in block 2 on the Cisco one. You're going to understand better how these routers work, right? So router join two or more networks and pass packets from one network to another one, right? The switch don't pass the packets from one network to another one. He just switch the frames between the devices. He switched the frames. This is what we call it switch. Right? But the router, he route the packets from one network to a different other network. Routers are responsible for determining the next network to which a packet should be forwarded. Right? So he's the one who's gonna identify that no. I need to send it to this one. If I want to go here, he's the only one that he can get me in there, right? This is why he didn't send it to this one or this one or this one or whatever. So they can identify what is the next router that I have to send to, that he gonna lead me to that final destination, right? Because he know what is the final destination. So as I told you, he zoom out and see the picture bigger, right, than the switches. So a typical router has internal processor, of course, an operating system, memory, input, output, RAM, whatever. This is why the routers are computers. They are considered as a computer. Here we are using a computer, not as a switch. Switch is kind of automated software that it's just plugged in some kind of motherboard and do switching those packets and it's done. But those ones are computers, right? This is why when we studied also the cables, for example, right, straight and crossover, we said that we when we connect a router to a computer, they are same, right? So a router to computer, we need a crossover instead of a straight, okay, because they are considered as computers. We are connecting same devices, homogeneous. Gateways are other routers. Those are routers also. So in the routers we have internal routers, the ones that they belong to one ESP, for example. We have border routers. Border routers, the ones that they talk to the backbones of the internet. So we're gonna talk about it on module 5, of course, next module, the one. But imagine if there is the network of I don't know, Bell or Fido or Videotron, right? Well, they have mini routers, but to go somewhere else, they need to go to the backbones of the internet, and there's other companies that they are handling those kind of connections, right? Till we go to other distribution ESP, all the ESPs on the world, they are all connected and they have all their own network. Those are internal routers. The gateways, the ones that we have here, the ones that we're going to find on the edge to go to the internet. So the real internet, I mean the backbones of the internet, right? We can find our destination here. We don't even need to go there, right? So if I'm connecting from home here and going to my ESP and connecting to another that is in the same ESP here, so it's going to be quick right here, right? But those here, those routers that they go to the backbone of the internet, we call them gateways or border routers. They are special and different than those ones and use different protocols to be able to use the protocols of the backbones here. This is external protocols or ABP, right? Here it's AGP or OSPF or whatever internal protocols that you're going to study on the block 2. So those, the ones that they open that door to go to this backbone, we call them gateways or border network. The ones that they handle the backbones here, those are called core routers. The core routers. Okay. They are bigger, much more bigger, much more advanced, and much more high speed and those stuff. So they are linking cities, they are linking countries, and so on and so on. Those are called core routers. They manage the backbone of the internet, the infrastructure of the internet. The border router is when any network, big company, whatever distribution company is using to get access to that infrastructure of the internet or the backbones of the internet. So we call them border routers. The ones that the ESP is using to route its own internal one, it's a internal routers, right? So we have those kind of routers that we call them border router or gateway routers. Connect an autonomous system with an outside network, for example, the router that connect to business with the ESP in a border router, right? So even here, for example, if I'm on my own business here, the router that I'm going to use to go in here and here, so you see, I'm having my own network and going long distance to go to this wall structure here. We get the router that you're going to handle this kind of communication going in here. We can call them also a gateway or a border router, right? So connecting two different forms of networks, those routers that we're going to find at the limit, the door to go after some different technology after using another network, we call them gateways or border routers. The ones that they maintain and handle all the infrastructure of the backbones of the internet, we call them core routers. Those are core routers, and those are internal. And here in AirSync, for example, I can have router or two linking all the classrooms. Well, those ones are internal in my organization here, right? And the protocols we use here, the protocols we use here, and the protocols we use here, and the protocols we use here are all different, right? For routing, so each level have his own technology, his own protocols of routing, and so on that we use. Collision domain and broadcast domain. We talked about this briefly, right? The collision domain is where the packets are subject to collide, and it happened, right? So it happened everywhere in all the network where we have this possibility that the packet's gonna collide. When the packets can collide is when we have two directions of communications from one destination to one source. For example, if I take this one here and I want to identify what is the collision domains here. You see, this computer to this card here, this is one collision domain right here. This one is one collision domain. This one is one separated collision domain. This one is one separated collision domain. This one is one separated collision domain. From here to here is one separated collision domain, right? So the switches, now we can identify them by another thing that they do. The switch separate each connection or each link to its own collision domain. So we reduce here the probabilities of collisions compared to the hub. If I'm using a hub, what we said about the hub is just forking the signal, right? So if this one is talking with this one, he is talking with everybody. And imagine this one is talking with this one in the same time, right? So he's talking with everybody. So here under the hub, the packets can collide everywhere, right? If this one is talking with this one and this one is talking with this one, they can also collide because there is no separation here, right? So the hub, all of it is one collision domain. But the switch, he's gonna separate each link to its own collision domain, reducing this complexity of collisions. So we can manage each one separately by itself, right? And here it's a huge collision domain. It's bigger, right? Broadcast domain is when we can broadcast something and we can receive it somewhere, right? So all that area, we call it a broadcast domain. So if someone, if this machine, for example, talked with the broadcast address, even the other switches, if they are linked to themselves, they can receive it. So we can identify all this zone as a one broadcast domain. This is also one broadcast domain. Now, what is the enemy of this broadcast? A router. Router never broadcast. The routers, when they receive broadcast, they will block it. Right? This is why when we use no type MP4, MPB, or hybrid, you remember when we said that when we have some NetBIOS names here and we want to resolve them here, we're going to need a Win server here. Because we still can resolve the names in the broadcast domain here. But if we're going to make a router somewhere, we will not be able to broadcast anything in the other area. The routers, they block broadcast. This is the role that you have to live with, right? Routers, when they receive a request of broadcast, they block it, they kill it, they kill that signal. They never broadcast, right? So we can broadcast from here to here because we pass through a router to communicate with that zone. And router is going to kill that broadcast from here or from this side, right? So this is one broadcast domain. This is one broadcast domain. This is one collision domain. This is one collision domain right here between the switches because data flow into both directions. So we can have packets that they collide. This is one collision domain. This is one collision domain. It's a hub. This is all one collision domain. This is not anymore switch, it's a hub. This is one collision domain because it's a switch and you see that it's connected just with a switch. This is one collision domain. Here it's one collision domain because the data can flow from here and go here and that's it. But they can collide here. But if I have this computer talking with this computer and this computer talking with this computer here, you see that the switch going to separate that. Those data transfer here and those data transfer between those ones, they will never collide, right? Because the data will flow here and this one, the data will flow here. But once the data going to come here and enter that hub, if this one is talking with this one, they can collide with the communication of this one because here is just forking the data, right? Forking the signal. So this is how we identify the broadcast domain and the collision domain. You have all the explanations here that you can read after. But this is the main idea here that you need to know. The switches separate each link or each communication differently than the other in a separated collision domain. But the switches don't block the broadcast. So if they receive a broadcast, they will just broadcast it again to the wall or the side, right? So if I send a broadcast here, this one gonna broadcast it, and this one gonna broadcast it, and so go on. Okay. But the router, when he receives that signal of broadcast, it will kill it. It will never go to the other side. Okay. So the switch, they separate each link to their own collision domain. The routers, they separate the network on different broadcast domain. Switches separate the network on different collision domain. Routers, they separate the network on different broadcast domain. The routers, they separate the network on different broadcast domain. Switches separate the network on different collision domain. Okay. This is some designation of the IEEE, or the Institute of Electrical and Electronical Engineers, that they made standards for many things. So Institute of Electrical and Electronic Engineers, a professional society that developed national and international standards to a variety of technical areas. The wireless technology, its identification is 102.11. So when you see this notification here, you know that you are dealing with wireless. All the Ethernet is .3, 802.3. This is the norm of the wireless in the standard of the word. This is the norm. If you want, it's a serial number, or it's a well, because we have the RFC, so identification of everything, of each norms, of whatever. So this is kind of a chapter in there, right? So everything that is related to wireless, you're gonna find it under this number. Okay, everything that is related to the Ethernet, things that they are cabled on the Ethernet, they are under this sequence of number. So this is the standard of the Ethernet. This is the standard of the wireless, right? Wired one, wireless one. Collision domain, how we solve the problem of collision domain when this happened. Of course, we have carrier sense multiple access collision avoidance, CSMA-CA. This technology, we use it on the Wi-Fi. This is the wireless way that our devices talk when they are on the wireless. So I have an access point and devices are talking to each other. They all pass through this access point, right? They all pass through this access point. So when they will need to talk, they're going to talk here and talk again, and so go on. But the collisions in themselves on the wireless technology, we use antenna to talk. And the antenna is a little bit different than the cables because it's either receiving or either sending, but it never do that at the same time. So first of all, from here to here, we don't have collisions, right? Can happen because of they are talking in one way at the time. It's a half duplex. It's not full duplex. Okay. Now we can use multiple antenna. This is usually what we use, and here multiple antenna to talk and receive in the same time in two different antenna or multiple antenna. We call it MIMO technology, or multiple input, multiple output. But we use CSMA to avoid something more complicated. How this device gonna know that he can talk to this device or not yet? Because this one is talking to this one, and this guy here, he don't see this one. This is what we call the ghost phenomena. So this device, he don't know that this one exists. Or even more complicated than that. Imagine my Wi-Fi is bigger, so I have an app access point that is connected to another access point that I have all the devices here. Right? This is much more complicated. So everything is hidden in the wireless. This one is hidden to this one, and we don't know if who is talking with who, right? So we don't know if there is a communication there yet or not, right? To send something, right? So to do that, so this one is talking with this one. He gonna always also broadcast some signals saying that I'm not available. I'm talking. So this one will not send anything, right? Now, once it's available, he will give him the right to talk. And when he talk, this one gonna say, I'm talking, right? And so go on and so go on. So this is kind of revealing the devices around, right? This is called it carrier sense, multiple access. So we can have multiple access to the medium to talk, and collision avoidance, because they don't happen. Using this technology, we don't have collisions at all. We can't have them, mainly. CSMA-CD is where the collisions, we can't avoid them. They happen, right? In the cables, for example, right? In the cables, in any collision domain. This is a big problem, right? So how the devices deal with this situation when the collisions happened, using this technology that is programmed in the network cards, if you want. This is the base of the Ethernet. One of the parts of the Ethernet called CSMA-CD, so carrier sense, multiple access collision detection. So what is this carrier sense? Carrier sense is we listen if there is a communication in there or not. So to be able to talk, right? So this is carrier sense, right? So we have kind of a sensor that we know that, oh, the medium is available now. I can send. There's no data flowing in there, right? So we can, they can use sensor to know if there is communication. So they will not send. Of course, they are receiving, right? Or they can know that the medium is available. There is no communication. I can send something in there, right? Multiple access, so they can do it multiple time, right? So they can check and dive every time, right? Collision detection is different than the collision avoidance. Here, collision detection. So the collision gonna happen. We can't avoid them in this kind of environment. Collision detection is when they happen, we have the technology to detect that situation, that when the device, the network card gonna know that, oh God, we had collisions. Because they carrier sense exactly at the same multi-nanoseconds in both, and they send packet, so collide, right? We have collision in there, right? It's really quick, and we are talking about really high frequency here. So we're not talking about collision of two cars or something, right? It's just bits of electricity on those packets. So we carry sense, okay, it's empty. We send, puff, collision. They are equipped with the technology to detect that when it happened, right? So collision detection. And this collision detection, when it happened, there is always a program in the background that will be executed right after to avoid it on the next send. Because if it happened, the network card, they're gonna use an algorithm to randomly generate a different timing, right? Using that algorithm, that the timing gonna be the same. It's kind of probability of epsilon, really small, right? So they will always generate another microsecond to send and receive a different way, right? Not that the same, exactly same atomic second, if you want, right? So this collision detection can detect the collision when they happen, and when they happen, the Ethernet is equipped to resend the data again, because they collide, so the data is corrupted, so they will send it back, but always in different timing now, right? So they will generate a different thing. They will be able to send it and avoid on the next send, avoid the collisions. Okay. So CSMA-CA is for wireless Wi-Fi. We avoid the collisions. We get more specific understanding about the devices around us, who is talking with who, right? Is managing this. CSMA-CD, we can detect when the collision happens. So this is Ethernet, this is wired, right? So we can detect the collisions when they happen. And once they happen, we are equipped with the complex system to avoid it on the next transfer of data. Okay. Now we're gonna go to the headers of each portion that we covered on the OC module, right? We're gonna start with the TCP segment. Remember when we talked about the TCP segment, we talked about which layer of OC module, guys? TCP segment, where is it? Which layer of the OC module? TCP segments, when we have segmentation of data? 4. That its name, the name of that layer, layer 4. What is its name? Transport layer. So on the transport layer, if you remember, I told you that we have all the payload and the data that it's coming from the upper layer, that is the session here. So we have all those headers, and after we're gonna put a header here, TH. Remember that? TH. And after this TH, go to the network layer when we are talking about the encapsulation. So all this now with the TH, TCP header, all those information that we encapsulate, they will have another header here of the network. This is a network header. So we're gonna encapsulate on top of it. And after that, which layer I have here? Write down the network. There's layer 4, this is layer 3. What is layer 2? Layer 2? Hello? Data link, yeah. And on the data link, we have exactly the same one that will be sent here. TH and NH. And here we're gonna add something completely different. Here we're gonna add a header of data link, so DH here. We're gonna encapsulate all that header, and we're gonna put also a footer, right? FH. That is a CRC, cyclic redundancy check, or we can call it also frame check sequence, right? So this is for detecting the problem of the frame when it transported on the layer physical, if it was corrupted or not, right? So when we have this here, right? In this layer we call it PDU, protocol data unit. So when we talk about the protocol data unit of transport, we can say that that is called a segment. It have a name, right? Now, as you can see, this was being transported here, right? So not really transported. We are just on the process here. We can say transport, but it's processed on the next one. So when it's processed on the next one, it becomes the SDU of that layer, service data unit. Right? So if we take the SDU and we add the NH here, the network header, this gonna become the PDU of the network. So all this will become the protocol data unit of a network, PDU of a network, right? So, and the PDU of the network will be processed again on the next one. So if we take this one and we put it here, this one become the SDU of the data link. So the PDU of each upper layer becomes service data unit to the next one, right? The protocol data layer of each layer become the service data unit of the next layer. And here when we add the data link header and the footer of the data link, we're gonna build the PDU of the data link that also have a name. This is a frame, right? So we can call it a frame. Okay. So if we talk about the SDU of the data link, it's the packet. It's the packet who come there and become the service data unit of the next one, right? So this is a packet. Okay. So as you can see here, we have each header in each one. And in our document, this is what we're going to talk about, the content of each informations that we are encapsulating in each one, right? So in each one, we're going to see by details what is inside this, what is inside this, what is inside this, and what is inside this. Okay? So in each one, we're going to see what is inside each, right? So you remember, this is PDU of here. When it go to be processed by the network layer, it become the SDU of that layer. We add the NH, it becomes the protocol data unit or PDU of that layer. PDU of that layer, again, processed on the data link, it becomes the service data unit of the data link. Now, once we add those informations, we have the protocol data unit of that data link. Of course, they have names. This one is a frame, this one is packet, and this one is a segment, right? This one is a segment. Now, let's go and see what is on the segment here. Right, so the segment header. See, segments. And we're gonna take just the header, right? So this is my data. So I'm gonna put it here. And this one. All right. Oops. All right. So here in front of us, the data here, this is the green part here, right? And all this top here is just this red part here. So we're gonna talk about this red part here, what is inside. You get it, guys? So this data here that is represented on the bottom, this is all this green part here, right? And all this here is what we are encapsulating to build a segment on top of that data, to segment the data. So as you can see, TCP header is the data from higher layers. So the green is coming from the session and presentation and the application. But when it come here, so we call it just data. So it's basically the PDU of the session, right? The PDU of the session that become here service data unit, of course, and so go on and so go on. So the PDU of the session here is the data form of higher layers, right? Plus the header of TCP, we're gonna build the segment. All right. So what is in here? So first of all, you need to see the length of it. It's all separated on 32 bits, 32 bits, 32 bits, 32 bits, 32 bits, all of it, right? From 0 to 31, and we have a frequency bits here. There is 32, split it on 16 on the middle here. There is another 32. There is another 32. There is another 32. There is another 32. And there is another 32. And after we put the data. Okay. So this is all the content of the header. So it's separated in multiple 32 things, right? 32-bit things. And let's see what is these things. So we have a source port. You remember TCP when we talked about the OC model? We said that this TCP layer is the one who handles the port number of the service. We are talking with port number 80, so it's web. We are talking about port number 21, it's FTP. 53, we are on the DNS, and so on. So this one handles the port number and handle the port destination on the other machine, right? So here, the port numbers are described by 60 bits on binary, and we can have all the numbers. And this is how port numbers can go from 0 to 55,555 or something like that, right? Because of its 2 power 16. If you type on Wikipedia port numbers, they will start talking about port numbers, and they will say to you, oh, well, they go from 0 till 65,000 something. Why? Because of they are represented by 16 bits, and 2 power 16, this is why we have this 65,000 something, right? And of course, from 0 till 1024, they are reserved. They are already reserved for specific protocols. So here we put the information of source number, and we put the information of a destination number, right? On where? TCP segment, the header. Just here. Right? Just in this top of information, the header of a TCP. On top of what? On top of the data. What is this data? Here it's the payload plus the application layer plus presentation layer plus session layer headers, right? So we end up with the PDU of the session. We process it again to the transport. It becomes the SDU of the transport. So it's all this green part here. It becomes the PDU of the transport and become all this part here, right? The green one. After, on top of it, we put this information. Okay, that's good. Those informations are the header of the TCP. This is how we build the protocol data unit of the layer 4, that we call it segment. We are segmenting data. All right. It handles first what? The most main part of that transport layer. It's destination port number, source port number. If we are using TCP header, because you remember, guys, on layer 4, we can have UDP, a datagram, and we talked about it. This TCP have, what is the difference between TCP and UDP? Come on, wake up. TCP and UDP, really important to know that. Come on, guys, I'm waiting for the answers. There you go. TCP connection-oriented Davinder. Good. So UDP is connectionless. No acknowledgement. Good. And you're going to know what is the acknowledgement and what is the sequencing number. All right? So here we have a sequence number and acknowledgement. This is how made this TCP communication. As you can see on UDP here, we don't have that anymore. Right? So this one is faster. Yeah, UDP is faster, but it's connectionless. We don't have acknowledgement. We are not sure if it reached the destination or not. There is no answer. We are not looking for an answer, right? But of course, it's much more faster because, as you can see, look at the difference. We don't have all this blah, blah, blah here. UDP, what we have destination port, source port, the length, how it's big, this header, and the checksum for it. That's it. Checksum is verification, right? So this is the datagram. This is what we call a datagram. You see how simple a datagram is compared to a segment of a TCP, right? And TCP, all those things that they are here, they use them for this kind of orientation, right? this kind of communication that depend on the answer of the other always. I told you, if you remember, TCP is, for example, when I say to a student, hi, how are you? Well, first of all, he's gonna tell me, I received your question that you told me, hi, how are you? And after he will answer. But me, when I receive it, I will tell him, I received my question, and I received your question, and I'm fine, thanks, right? So there's always acknowledgement of something. We acknowledge that we received something, right? How we acknowledge those things? By this sequence number and acknowledgement. They are coded on 32 bits and 32 bits. As you can see, the length of the sequence number is 32 bits. And acknowledge is 32 bits. UDP broadcast. We use UDP on broadcast, but it doesn't mean that UDP is the broadcast, right? UDP, the broadcast is an address where we're going to send something, right? But UDP is a datagram. We can send it to one destination, not all of them, right? We can UDP something, right? All right, so here's how this sequence number synchronization work. We have ACK and SYN, right? So synchronization and acknowledgement. This is how this handshakes happen, right? On the connection oriented. This is how we orient the connection always and acknowledge things using this 32 bits here and 32 bits here to know what is the number, right? And using also flags. We have here the flag of ACK and we have here the flag of synchronization. If we say that we have an incrementation on the synchronization, this flag gonna be 1, not 0. Those all are 1, 1, 1 or 0, right? So those are 1 bit. Urgent, ACK, the push, we're gonna talk about them, right? And we have fin or end, and we have synchronization and reset and push, acknowledgement, urgent. So if we have an acknowledgement that happened here, this one gonna be 1. So there is an acknowledgement here. If this 32-bit will be also incremented on synchronization, we have 1 here. So we have a synchronization in there. Those are just flags to say that we have something. You see, if I have 1, I know that I have some data of urgent pointer here. I'm gonna have some data right here, right? So all these are 1 bit, 1 bit, 1 bit, 1 bit, 1 bit, 1 bit. I still have here, how many? 4 bits. So 2 here and 2 here, because I have 16 in all this part is 16, right? All this part is 16. Now let's talk about this 2, just 2. We go here, we see that this is a computer, so he's gonna generate a sequencing number. We have a sequence number. ACK is 0. We don't have any acknowledgement yet. We are just talking. We're just starting talking, right? So it's ring, ring, hello, right? It's the first one. So he will generate the sequencing number and he will put it in here and he will flag this and he will send it on the segment. Now this guy, when he gonna receive it, look at what happened. This sequencing number, he will increment it. He will take the number, you see 58, it becomes 59, and he will put it on the acknowledgement, right? So now when this guy gonna receive his sequencing number incremented by 1, he will know that this guy received it. This is the connection oriented. And this guy now is talking to this one. So he needs his own sequencing number, right? So he will take the sequence number of the other, he will put it on the acknowledgement incremented. This means I received it, right? And he will put his own sequencing number, a new one. You see a random one. Here you go, 2 totally different. And he will send it. He say, hello. So this is an acknowledgement. All right, I received your hello here. This is Mark. He's representing himself. This is the synchronization here, right? And this guy, when he's gonna receive that, he's gonna send some data. What he gonna do? He will always, to acknowledge this, that he received this, he will take that sequencing number, he will increment it on the acknowledgement field here, or acknowledgement block. and he will send back his synchronization number, the acknowledgement that he received from here. He will not increment it. He will just send it back as the next sequencing number. So you see that each part have a sequence number, and each acknowledgement is the incrementation of the other part acknowledgement number to tell that I received it, right? Now he's sending, you see what he did? What he did? He took the sequence number of this one, he incremented +1, so it was 69, he put it 70, and he sent it back as an ACK flag right here, right? And this is how communication on TCP happen. We always take on consideration this sequence number and acknowledgement in our segments, that they are transformed to packets, to frames, and to bits after. All right. TCP point-to-point, UDP broadcast, TCP provide guarantee delivery. Yeah, this is the guarantee of the delivery, because if when we receive without incrementation, right? When we receive something without incrementation, or we didn't get any acknowledgement from the order here, so this wasn't incremented, this guy, what he gonna do? He gonna ring again because he know that this one, we had a problem. He didn't receive it, because if he receive it, I'm gonna have an incrementation here, right? So if the data here was good, I'm gonna have an incrementation here, right? So didn't increment it, there's no ACK. Okay, I'm gonna ring again, tell I'm gonna get an acknowledgement of that message here, right? And same thing here, when he sent back, this guy, if he didn't receive the acknowledgement of his sequencing number back, he will still say, hello, this is Mark. He will send it again, but because he know that something weird happened with this, he didn't receive it, or otherwise it will be incremented. My sequencing number will be acknowledged. Acknowledged, it means that it changed from sequence to acknowledgement, and the number was being incremented, right? So this is how we acknowledge things on the TCP header. You have a table explaining all this, right? So you have 16 bits here on the source port. So this is my source port. What he's saying, indicate the port number of the source node. Destination 16 indicate the port number of destination node. Sequence number, identify the data segment position in the stream of the segment already sent. This is the sequence number, and those, of course, they are generated on the data stream position, right? So we have a flow of this stream, and one is next to the other one, one is next to the other one. Acknowledgement number confirm receipt of the data via return message to the sender, right? So we acknowledge thing, we confirm that we received your sequencing number, right? This sequence, this packet identifier, that sequence number of this stream, of this data stream, I incremented it. So I get it. I don't need it back. We just can go forward, go for the next ones, right? It's same thing like here. So if we have, for example, a data stream that I'm sending, and let's say this is P1, right? And I had an acknowledgement of P1. So P1 plus 1, I will name it like this. So this is an acknowledgement of it, right? This is the sequence number of it. And after this guy here, when he received, he doubled the stream, right? So now he's going to save P2, P3, and I get an acknowledgement of P3 plus 1. So you see, they identify the stream here. The sequence number gonna identify the stream position of the segment, right, on the data stream. So I received 3 plus 1. Okay, so 2, of course, it was received. Otherwise, I will receive directly the 2 plus 1 here. If I had a problem with 3, he will acknowledge just the 2, right? Okay, let's double it again. So if he can take it and double it, he will send now 4 streams, for example, right? And we're gonna have P4, P5, P6, P7. So this is the sequencing number of each one. Now, it depends on the incrementation of the acknowledgement of that position of sequencing number on the stream. He will know what was being received or not, right? So if I receive acknowledgement P7 plus 1, well, that's great. He received all of them. But here, instead of receiving P7 plus 1, if I'm going to receive P5 plus 1, the next stream that I'm going to send here, he will restart from P6. Because he didn't acknowledge P6 and P7. Something happened bad here. So P6, P7, P8, P9, P10, P, and doubling, always doubling those things, right? But I will start from P6 because this is the only acknowledgement that I received here, okay? So this is how this sequencing and acknowledgement happen. TCP header length. Indicate the length of the TCP header in byte. So here, this part here, it's gonna indicate on byte how many byte we have on all this TCP header length. Reserved, indicate the field reserved for later use when we need to put something plus on all this header. We have all the flags. Urgent, what is urgent? Urgent is just an identifier of some kind of type of segments, right? They should be treated on with some instructions. They should be treated with some instructions. What is those instructions? They should be here on the data. How we can find them? We have an urgent pointer. This urgent pointer show us where is this instructions of this urgent thing here in the data, so the computer can go in there and read this data and treat those segments specially based on what is the instructions of that urgent things, right? So when we have a flag 1 here, this means we have urgent thing, and the urgent pointer gonna have some address here on this bits frequencies, right, on this data. The urgent, it doesn't mean that they have higher priority, right? Urgent, it means that they need to be treated specially. There is something special in there that you need to read the instructions here to know how to deal with them, right? This is the urgent, right? But it doesn't mean that it have higher priority than the others. The higher priority is more than this, the push. Push, this means you don't put this on the buffer, just push them to the application directly, right? So they will not go to the buffer of the TCP. They will not wait on that stream. When they receive something and the push here is 1, they will directly send it to the RAM inside the application, right? So this means push it to the application directly, no buffer, right? No buffer. Reset, this means something happened with this sequencing number here. We need to reset the communication and to synchronize our numbers because we are lost now. I don't know what I did increment or not. Something weird happened here. So when the machine gonna ask to reset this sequence and acknowledgement number and start over, right, with this incrementation things, they will push. They will put a 1 bit here. So if they put it, they are asking for a reinitialization or a reset of those bits here. And synchronize, this means that this sequence number have something. So we incremented it, we put 1 here. Acknowledgement, we talked about it, same thing. And this is the last one. So I'm asking to finish this TCP IP communication. If I put this one as 1, so this is the last one, right? We're not talking about, there's no more any synchronization or acknowledgement, right? Fin is the last, right? So I'm asking to stop it. I'm asking to stop it, or I'm telling that I did stop it, right? In this way. So this is all the flags. So TCP header here saying what is the length of it, reserved for some further informations if needed. Urgent pointer 1. This is the pointer after. So if we put 1 here, this means we have urgent something here, and the urgent pointer is going to point in there, right? And all the flags that I explained to you, you're going to find the explanation 1 by 1 right here. You can read it after. So they are all identified by 1 bit. The urgent pointer field later to the segment contain information to the receiver, so specific information with this segment, how it's going to be treated. There's an algorithm in there, how you're going to execute it, or specific instructions. So if it's 0, this part will be ignored, right? This part will be ignored. You know that there is no urgent, so all these 16 bits, they will be ignored. If it's 1, they will take on consideration, because you know, guys, here in reality, what is it? It's just bits coming, right? So all this is kind of logic that we are putting behind to understand those bits, what they mean, and how we're gonna treat this data to build it back, right? So if that bit is 0 here, so we're gonna count 32, 32, 32, and this 4 here, and that bit is 0. All right, so I will directly go to option. I will not take on consideration this one. So the next bit that they are coming after checksum, there will be options. There will not be urgent pointer. I have a bit here. All right, so checksum next 16 bits, it's the urgent pointer. So you see how logic is complex, this thing, and wonderful, right? So all the flags can be on or off, and each one have his own objective, of course. The fan here is the last in the sequence of a connection. Sliding window or size of window indicate how many bytes the sender can issue to a receiver while acknowledgement for this segment is outstanding. Remember here I told you is doubling, but in reality it's not always doubling. Is this guy is always, when he's answering, he's telling on that size window how many he can go more than the first one, right? So sometimes if you're gonna tell him send me double, he will send double, right? If you're gonna tell him you can send me more than double, triple, he will triple, and so go on and so go on and so go on, right? So this is how what is the capacity of that bytes that I can receive on the next stream, right? So indicate how many bytes the sender can issue to a receiver while acknowledgement for this segment is outstanding. This will perform a flow control. So this is the slide window, and we control that flow, right? So we the data flow, we control it by this sliding window bits. Checksum allow the receiving node to determine whether the TCP segment became corrupted or not, right? So it's kind of the same as a CRC. It's a little bit different, not a little bit, much more different completely. But these 16 bits contain an algorithm here to let the receiver know that it was corrupted or not. This one, when we generate it, we're going to find a number, and we're going to calculate something about all this, and we're going to find a number. If those two numbers were different, so something were corrupted during the transportation, right? It's something like that, but much more complicated, using math in there. So we have a checksum here that we can know if this segment is corrupted or not. This is exactly the sequence that was being sent in there, the one that I'm receiving it in here, right? Checking what? Checking this checksum here. After that, you have urgent pointer. We talked about it. The option is a special option such as a maximum segment size a network can handle, right? Here, when they're going to start talking, they're going to deal with these options. All right, me, I'm a, for example, I'm a network card of 10 megabits, right? Or 100 megabyte. The other is 1 gig. Okay, so we're gonna set up these roles and our options. How we gonna talk? I can receive size of segments maximum 10 kilo. 100. Me, I can deal with 100 kilo. I'm not strong, right? The other one, he can say here, okay, me, I can deal with 1 ton of data, right? And so go on and so go on. So all those special informations that we have to take on consideration about the other side and our side. So we're gonna this is my capacity, this is your capacity of segment, right? In byte. This is my capacity that I can take. This is your capacity that you can take. They will put it in here so they know, okay, me, I'm really strong. I can talk with 100 kilo, but the other guy can deal just with 5 kilos. All right, so I will take that on consideration in my option. Okay, so is my segments will never be bigger than 5 kilo at one, right? And so on. So he can handle them. So specifies special options such as the maximum size of the segment that the network can handle. The padding is tricky because of why? Because of here, we need to finish exactly with the double of 32. right? With a double of 32. And those informations that they are here, they can be completely different. Sometimes we don't have urgent pointers, sometimes we have urgent, sometimes we have this, sometimes we don't have this, and so on and so on. But we need always to finish with the double of 32, right? So this header here should be definitely a double of 32 in the TCP IPv4, right? So what we do in this case, we put a padding here. Just in case we put it all the essential informations, and we still need something to be a double of 32, so we're gonna put here blah 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 blah, something that doesn't have a meaning at all. It's just a sequence of bits, but we still keep it double of 32, right? So this is padding. It can be 0, right? If we put all the informations and we fit with the option here exactly 32, we don't care about the padding anymore. It's 0. The padding gonna become 0, right? But the more we are missing bits to go to the double of 32, this padding gonna take fake bits in there just to fit, to keep it on the shape of 32, 32, 32. So this is the padding, right? So padding contain a filter information to ensure that the size of the TCP header is a multiple of 32 bit. That's it. And after we have the data. What is this? This is the SDU, right? So service data unit of what? Of the session. So on the session, we call it PDU. And it contains all the headers of the session and presentation and whatever. So this is all this green part here. This is all this green part here. And now we covered this header, right? So we talked about this header and we saw what it contained. And if it's UDP, as you can see, we don't have much. We have the length that we have on TCP. So what is the length of all this header? We have source port, we have checksum, and we have a destination port, and there is the data. That's it. So you see, it's much more simple. We send, we don't care. There is no acknowledgement in that kind of communication. There is no options. There's nothing. I just want to carry this data from somewhere to somewhere, and they don't care. They didn't save it. They didn't save it. We are not in a date, right? This one is dating with the other device, if you want. But this one is just sending a bottle in the ocean, right? And maybe the ocean gonna take it to a destination or not, right? I'm gonna put a name in there, and I will put it in there, and I will send it based on what? Based on this source port and destination port, and that's it. Okay. So after that, this one gonna go to the TCP packet, or this one gonna go to the TCP packet. Okay, to put that blue header now is our next topic. So we're gonna need to deal with this, right? This NH. All right. So it depends here if it's TCP segment or it's UDP datagram on the transport that it was put it in here. So if we put it just the source port and destination port and the length and the checksum in here, so this become a datagram. If we put it all these informations in there, this become a TCP on that segment. All right, guys. So if you have any question about this, please ask your question. Or otherwise, we're gonna stop here and take a little break because it's almost 10:30 here. We're gonna take 30 minutes of break time, and we come back right after. If you have any question, please ask your question. After that, we're gonna see what is the header on the packet, right? So we covered the layer 4 transport. We saw the segment of layer 4.